The smaller flares, the less strong flares not always accelerate particles, and it's kind of difficult to predict when they will accelerate particles and when not. And so this gives rise to what we call solar energetic particle events, SEPs. And so, in fact, coronal mass ejections can also accelerate particles, because here you see kind of a cartoon of a coronal mass ejection. You have the leading shock front, and then there's a kind of magnetic cloud, of like a flux rope, a magnetic flux rope. And this shock front also can accelerate particles. In the shock front there, we have some models that can actually explain why the particles can be accelerated up to certain energies. And because it are charged particles, these are ions and protons and electrons. And so they, of course, see the magnetic field, and so they propagate along this Parker spiral, so these magnetic field lines in the heliosphere. It are electrons, protons, and ions, as I mentioned, and they have much higher energies than the background solar wind particles. So they can be up to giga electron volts. So 1 mega electron volt proton is traveling at 14,000 kilometers per second, and a giga electron volt proton is traveling almost at the speed of light. Yeah, so 262,000 kilometers per second. So much more energetic than the background of solar wind. But they are charged, so they see the magnetic field and they follow this magnetic field. Now, when these particles reach Earth, they can be very dangerous because they are accelerated, so they radiate energy, and so this radiation can be very dangerous for us. And this brings us to the effect of the sun at Earth. It's of course very important, the sunlight, for our daily life, for the existence of life at Earth, but it's also threatening Earth. And this is the definition of space weather in the National Space Weather Plan of the United States, the strategic plan. And it says that space weather refers to the conditions on the sun and in the solar wind, but also in the magnetosphere and the ionosphere and the thermosphere of Earth, that can influence the performance and the reliability of both spaceborne and ground-based technological systems, and can endanger human life or health, which is to do, of course, with this radiation. Of course, at the solar surface, at the Earth's surface, we are protected by the atmosphere of Earth, and also by our magnetic shield, the magnetosphere. But the higher up you go, so the less thick this protection layer is, and the more vulnerable you are to radiation. For instance, if you are in an airplane, in a transatlantic flight, you go through these 67 degrees north or south, you can get good doses of radiation if you do that during a geomagnetic storm. And also, of course, astronauts, if they go to the International Space Station, they are actually out of the atmosphere almost completely, and so they are very vulnerable to the radiation in space. So the corona is dominated by the magnetic field, and because the corona is very hot, the plasma is also completely ionized, and so the magnetic field, the magnetic forces, the Lorentz force, J cross B force, well, this is the magnetic part of the Lorentz force. There's also an electrostatic part, but it is ignorable. So the J cross B force is very strong, much stronger than gravity in the atmosphere of the sun, because well, gravity is on the sun much larger than at Earth, yeah? 27 times, because of the radius of the sun is also much larger than at Earth. The mass is, of course, much larger, but the density in the corona is very low. So the force, the gravitational force, is the density times the per unit volume is the density times the gravity. So in that sense, because of the low density, it is not that important. The Lorentz force is most important, and so. You have these dynamic events that I mentioned, the flares and the coronal mass ejections. They can be huge. So this is to scale the Earth, and this is like one of these loops that you can see in the corona of the sun that can sometimes stay there for many months, like this one. This is a very famous one that stayed for many solar rotations. The sun rotates like in 1 month on average. It's a well, not rigid rotation, so it's kind of well, it rotates faster at the poles and at the equator than at the poles. But so it can stay there for several months and then all of a sudden become unstable and then create a huge coronal mass ejection. And this is actually the underlying physics is actually because there's no magnetic monopole. So the magnetic field is solenoidal. So the divergence has to be zero. And as you know, if you write this down in spherical coordinates, you see that you cannot have a spherically symmetric magnetic field. So gravity tries to make the star spherically symmetric, but it is impossible because of the magnetic field. And so there's a constant fight between gravitational force and the Lorentz force, and often the Lorentz force wins, and then you get these huge ejections of plasma. And these create this what we call the coronal mass ejections. Here you see a speeded up movie of 1999 August, month of August, the whole month of August. You see that this was during solar maximum. So there are a few CMEs per day. Of course, not all the CMEs affect Earth. Only when you see a so-called halo CME all around the sun, it means it is going in our direction or in the other direction. And these halo CMEs are the ones that are potentially dangerous because they are hitting the Earth. But actually, like 10% of all the CMEs have some effect at Earth. And so that means more than one CME per week during solar maximum. As I mentioned, the velocity of the CMEs can be up to 3,000 kilometers per second. The mass of the CME is huge. Yeah, the big CMEs have like 10 to the 16 grams of plasma. I was told this is comparable to the mass of the Himalaya. Yeah, so this is a huge amount of mass that is ejected to very high velocities. So this is involving an enormous amount of energy. And the big solar flares and the big coronal mass ejections have an energy of 10 to the 26 joules, so 10 to the 33 ergs. So this is huge. This is several thousand atom bombs, actually. Nevertheless, so these are the most violent phenomena that are occurring in the solar system. Nevertheless, they were named only or rediscovered only fairly recently in the 70s during these OSO 7 missions. And the first time coronal mass ejection was used, this terminology was by Bruckner in 72. Although there are ancient images of Chinese observations of coronal masses, because if this normally you cannot see the corona because of the blinding light from the photosphere, but during a solar eclipse, for instance, if there's a CME occurring during a solar eclipse, you could easily see it with the naked eye. Actually, these what you see here are synthetic eclipses made by so-called coronagraphs, where they can put a disk. This is a disk that is put on the disk of the sun. Here is the sun, and so you can then see you kind of blind the light coming from the photosphere, and then you can see the corona in white light with a naked eye. Now, so when they hit the magnetosphere of the Earth, they have a lot of negative effects. The coronal mass ejections are one of the major drivers of space weather, and so you can see they have, of course, effect on particles in the radiation belts, and therefore also the astronauts. The astronauts, when they are in the International Space Station, they are protected. Yeah. But outside, when they do an extra vehicle activity, so then they are not so protected, and so then they before they do such an activity, they actually watch the space weather predictions, because if they would do an extra vehicle activity during CME that passes by, they would get like 50 millisievert radiation, which is like a huge amount. Because the maximum during the whole 6-month mission is like 300 millisievert, and then they have to abort the mission. So they try to avoid it, of course. But also many other effects, like you can see here, there's a solar cell damage on satellites, enhanced drag, but also even at Earth pipelines, you get these geomagnetically induced currents, as they call it, in everything that is long and conducting at Earth. So pipelines, but also the power grid. There are peak currents in the power grid, which can actually burn down some power stations. Also, in long bridges, even they have measured these peak currents. Because the satellites are affected, everything that has to do with navigation and telecommunication is affected. So we are more and more dependent on this kind of technology. For instance, ships, 99% of the ships is completely automated and navigating on GPS. And so this is, of course, dangerous during geomagnetic storms. Airplanes also, they take off and they land on GPS. So this is kind of, getting more and more dangerous. And think about self-driving cars, which will be completely depending on GPS also. So this is going to be, we're becoming more and more dependent on this technology, and therefore the potential damage is getting higher and higher. And the reason for the Geeks ejection is visible here. This is a simulation of the magnetosphere of the Earth, and you see the wind is not a constant wind, so it is changing in time, and therefore the magnetic field is changing in time. And as you know from Maxwell equations, if you change the magnetic field in time, you induce an electric field in everything that's long and conducting. On the bottom, you see a movie kind of animation, artist impression of an SEP event. You see the magnetic cloud and the CME hitting the magnetosphere of the Earth, and then there's some reconnection going on in the tail, the magnetic tail, so at the back of the Earth. And because of these reconnected field lines, the particles can actually enter the Van Allen belts, and then if you launch a satellite through these Van Allen belts, you can lose the satellite, or the instruments on the satellite can be severely damaged because of these SEPs. Like what happened 2 weeks ago on the 4th of February, SpaceX launched 49 satellites, 40 were lost because of a geomagnetic storm at the same time, which was predicted, by the way. I don't know why they launched the satellites. Anyway. So there is a need for reliable predictions. I think I'm missing one slide. I don't know. Wait 1 second. Where is my? It's coming out. So there's a need for reliable prediction because we want to kind of avoid or predict the space weather to avoid some of the damage and the health risks. And to do that properly, we need actually a deeper insight in the physics behind the space weather. So the first space weather models were actually empirical models, and they were not so good. So they often gave an alert or an alarm of a CME that took off, and then there was nothing happening a couple of days later. Sometimes they missed it completely, and then there was a big storm. So now the models are more and more physics-based, and the prediction is getting better. But we, of course, need a lot of observations as input for these models. We need boundary conditions, we need initial conditions for the models. And there is a problem because observations are sometimes limited or difficult to interpret because of projection effects, for instance, or some things you cannot directly observe, like, for instance, the coronal magnetic field. You cannot measure the magnetic field in the coronal. You can measure it in the photosphere because of Zeeman splitting of spectral lines. You can, there are several techniques to use, but the emission from the corona is too weak to do this. So you cannot, you have no clue, no measurement of the coronal magnetic field. And this is where numerical simulation models can provide the missing information, the things that cannot be observed directly, like the magnetic field topology. The density, for instance, also, we have no clue about observationally about the density in the CME. So this is where we can do numerical modeling. And this is the motivation. And it is very necessary because I'm actually surprised of, I see slides that I don't expect, I'm sorry. So here you see how complex it can be. So you see that it's a complex system, this space weather. It's multidisciplinary also. And so you have these SEP events, you have the flares, you have the CMEs that propagate all the way through the heliosphere to the Earth. And during this propagation, there are CME interactions. You have also gradual SEP events in the shock waves of these CMEs. And then when they arrive at Earth, you get these geomagnetic storms. And so we try to model this, but it's of course impossible to model the whole thing as one. So what we do is we develop different models for different parts of this chain, and then we couple the models together to do global predictions. Okay, so the estimate economic cost is like 10 to the 10 euro per year. Yeah, this is on average. The normal space weather would cause this amount of damage at Earth. This is a recent estimate. And so what we are really afraid of is an extreme event. Yeah, extreme events like the Carrington event in 1859. That was a big solar flare. And okay, in those days there were no satellites, of course, so the damage was not so big. There were some telex cable stations that were burned down because of these peak currents in the telex cables. But if a storm like that, the one of 1859, would occur now, it would be a huge disaster. So estimates are up to 2.7 trillion euros of damage. This is an estimate of Eastwood et al. In 2017. And so luckily these events do not occur every year, so they would occur only every 100 to 200 years. But yeah, the last big one was in 1859. And then of course there's still a link to climate change, which is actually now being modeled also. So the global circulation models at Earth, they are now linked to space weather models to see what, because they actually assume that the input from the sun is constant, but it is not. And so now they try to take that into account, this ionization in the ionosphere, the changes because of the geomagnetic storms are now taken also into account in these global circulation models. So this brings me then to the mathematical modeling, and there are kind of three types of models that we can envisage. One is the motion of charged particles in a given electromagnetic field. And this is just the Newton's law. So the motion acceleration is by the forces. So you just solve these three differential equations per particle. But of course, in a CME, you have 10 to the 32 particles on average. So you cannot do that for every particle. So this is a nice model to get some of the effects, to explain some of the effects, like in a magnetic bottle, for instance, how this works. You can do that with these equations. But to describe a whole CME, you need actually to average. And so then you have the kinetic theory, which is studying a set of particles for a microscopic description in terms of distribution functions. Yeah, the distribution functions for the electrons and the different ions. And these distribution functions are functions of 7 independent variables: the 3 space coordinates, the 3 velocity components, and time. And therefore, these models are very CPU demanding still. And so they are used a lot, actually. This is the best model to describe a plasma. But if you apply it, even now, with nowadays supercomputers, we have to limit the computational domain to, for instance, this reconnection region in the magneto tail that I showed you. To study this reconnection, we have a narrow box, often 2D actually, but sometimes in 3D, but only where the reconnection occurs, and that you can describe in kinetic theory. But of course, there are now also models that are for the global magnetosphere. There are some models being developed for in kinetic theory, but they are very CPU demanding. They take weeks to compute on thousands of processors, so you cannot do predictions with these models yet. Yeah. So what we do when we want to do predictions, we need a continuum or a fluid model for a macroscopic description. So we average over the velocity components in the space domain, and so we end up with thermodynamic quantities like temperature, pressure, velocity, functions of only the spatial coordinates and time. And these macroscopic equations you can actually solve on a big computer, and can do modeling all the way from the sun to the Earth. And this is what my team in Leuven does. So here you see the equations of Magneto-HydroDynamics, just to show you, because I know that in your department you do fluid CFD, so computational fluid dynamics. Well, this is very similar actually. It's just taking into account the effect of the magnetic field. And so we can write the equations of Magneto-HydroDynamics as conservation laws, ideal MHD equations, at least as conservation laws. So they are nonlinear hyperbolic PDEs. You have here the conservation of mass, you have the conservation of momentum, you have the conservation of energy, where of course we have now also taken into account the kinetic energy. And here you have the flux conservation. This is the induction equation. This is the extra equation as compared to fluid. The other equation have extra terms because of the magnetic field. And here you have one extra, well, three, because it's a vector equation, three extra equations for the effect of the magnetic field. And this comes down to conservation of magnetic flux. Of course, it's not only, the model is not only equations, you also need a kind of geometry and then boundary conditions and initial conditions. But these are the equations we are actually solving. Well, these are the ideal MHD equations. We want to take into account the effects of viscosity or resistivity. We have, of course, source terms in these equations. Yeah. And this is the solenoidal condition is also an extra problem numerically. Because it has to be kept zero at all times. And of course, theoretically, it is not a problem because if you take the divergence of this equation, you will see that you will get it's conserved in time. So if it is satisfied at t equals 0, this equation, it will always be satisfied in theory. But in practice, due to numerical errors, you have to really take measures to keep the divergence of the 0 at all times. So this is an additional complexity compared to computational fluid dynamics. Now, so what we do is modeling of CMEs. We started off in 2.5D, so axis symmetric. And so here you see some nice simulation of one of my PhD students in 2018, which is with adaptive mesh refinement. Here you see a triple arcade structure on the sun. This is the surface of the sun. And so we have this streamer, helmet streamer, as we say. And so if you run it, you see that it changes in time. And we have here adaptive mesh refinement. So with 7 levels of adaptation. Here you see the log of the current density visualized. And here you see the grid colored by the current density. You see very structures occurring, magnetic islands, and how they evolve. And this is all possible to do with this kind of high resolutions in 2.5D. But of course, this is the real sun is of course a 3D. And so just a couple of years ago, we developed a new model, which is called EUHFORIA, which is an acronym for European Heliospheric Forecasting Information Asset. And it has 2 parts. It is based on a simple coronal model and then a model for the heliospheric wind and CME evolution. The coronal model is only there to provide the boundary conditions for the wind model. And we put the boundary of the wind model at 0.1 AU, so 10% of the distance between Sun and Earth, 21.5 radii of the Sun, because at that point, the wind of the solar wind is already super fast, supersonic, super fast. So there's no characteristics going back to the Sun, so the boundary conditions are easy to implement at that boundary. And to get these boundary conditions, we have this semi-empirical Wang-Shili arch model, as it is called. It is actually based on a magnetogram. So we start from the magnetic field in the magnetogram, we extrapolate that. So we assume magnetic field is potential, so it can be written as the gradient of a potential function. This B equals 0. This potential function has to satisfy Laplace equation. And as a boundary conditions, we at a lower boundary use this magnetogram, where we have values for the BR component. And at the source surface, so 2.5, 2.6 solar radii, we assume that the magnetic field is purely radial. So there we put the theta and the phi component of D equal to 0, and we can then solve the Laplace equation and find the potential field source surface model, as it is called, for the magnetic field. And then we have can Stefaan current sheet model to get narrow current sheets. And so we can this way then determine the magnetic field, the radial component of magnetic field at 0.1 AU. We also have a model then for the radial velocity at 0.1 AU, and then the density and the temperature are just by using some conservation laws estimated at 0.1 AU. When we have these boundary conditions, we can start the heliospheric model. And so here you see it's a 3D model, but here you see the rate of velocity and the density in the equatorial plane and in the meridional plane of the Earth. The blue dot is the Earth, and so you also see some other satellites. This is Stereo A, this is Mars, and you also have Venus and Mercury here. So you can visualize that, and you can then solve the equations in time. And you can superpose on this background wind. The sun is rotating, and you can see that again this spiral structure of the magnetic wind, of the magnetized wind. And then on top of that, we can launch CMEs, and then we can predict when the CMEs actually arrive at Earth. Here the rate of velocity, here the density. And we can compare at Earth. We have just before the Earth, we have satellites which measure the rate of velocity and the density and the temperature and the magnetic field components, and we can compare our synthetic data at L1, the Lagrange point just in front of the Earth, with the data of the measurements over there. So these models, the real challenge of these models is that they have to be fast. We try to do predictions, so the model cannot take longer than the CME itself. So the model, this is the reason also why we have a very simple coronal model. It converges in like 10 minutes. And the CME evolution takes like 1.5 to 2 hours in this EUHFORIA model. So we can do a simulation like, let's say 2 hours. The problem is that you do not, you're not satisfied with one simulation because there's some uncertainty on the input parameters. I will come to that later on. So the rationale is that we have, we want to kind of quantify the deformation and the deflection and the erosion of these flux rope CMEs during their evolution through the heliosphere, but we also want to characterize the magnetosheets, the region between the shock and the magnetic cloud in the CMEs, because we have some information from in situ measurements. And we also want to study CME interaction because they often occur. 2/3 of all CMEs are actually interaction of two CMEs before they reach Earth. And so we want to also quantify the effect of that on SEP production. But of course, we also want to do forecasts, and the novelty of our model is that it has flux rope CME. So we take into account the internal magnetic structure of the CME, which is very important for the geoeffectivity, the geoeffectiveness of the impact of the CME, because that is what was missing in the early predictions. So sometimes there's a big CME and it does not create a geomagnetic storm, and sometimes a small CME creates a huge geomagnetic storm. And the clue is the polarity of the internal magnetic field of the CME, because if it is, if you can see it as the magnetic polarity is the same as the polarity of the Earth magnetic field, the impact is very small because the two dipoles kind of repel each other. But when the Z component of the magnetic field, the component perpendicular to the equatorial plane, is negative in the CME, it hits the dipole of the magnetic field of the Earth, which is the other polarity, and then they kind of get together, and then they can reconnect. And then a lot of particles can actually enter the magnetosphere, and these are the most dangerous cases. So we need to kind of predict the Z component of the magnetic field of the CME when it arrives at Earth. Now we try to do predictions for missions. So orbital PSP are the new missions that are now ongoing. So it's a data-driven model. I already mentioned the magnetogram. We have different sources of magnetograms that we can use. And also the parameters of the CMEs themselves are actually determined from data using coronagraph imagery like GCS, Stereocat. There are databases where we can actually derive information from. And so we use this in different models of CMEs, and then we propagate the CMEs on top of the wind model. And try to predict what effect it will have at Earth. So what we have in EUHFORIA is data-driven flux rope CME. So we start in a simple model from a force-free SPHERMAC model that has been implemented in EUHFORIA in 2019 by one of my PhD students, Christine Verbeeke. And so this can predict the BZ component at 1 AU and therefore also the geo-effectiveness. Yeah. But the problem is that the SPHERMAC is a good model locally. So a real CME has a flux rope structure. A SPHERMAC is just a sphere, right? I mean, you launch it, but it doesn't have these legs. So if this would be Earth and it's a head-on impact at Earth, the SPHERMAC can actually model the CME parameters of this flux rope. But if the Earth would be here in the leg of if the leg of the CME is hitting the Earth, then the SPHERMAC is really very bad. We have very bad results in those cases. So we are trying now to implement flux rope models that are more advanced, more realistic than this, what we have here. The input parameters, there are many. Yeah, so for a cone CME, this is just without an internal magnetic field. We have 7 input parameters. There's a speed, insertion time, of course, longitude, latitude of the CME where it occurred, the width of the CME, the density, and the temperature. Yeah, and so for a SPHERMAC, we have 3 additional parameters, so 10 parameters in total. There's a flux rope tilt, the helicity, and then the flux of the magnetic field. So these parameters can be derived to some extent from images, like you, for instance, here you see from StereoCAT, you have two different times, which are like, what is it, 48 minutes from each other. You have the CME, white light image of the CME. You can estimate the width of the CME, and then from these 2 images in different times, you can estimate how far it progressed in time, and then you can derive the speed of the CME, for instance. And so this is the way we try to use this input and to determine these CME parameters. So for the first 5 parameters, we can do this 3D reconstructions with the graduated cylindrical shell model, GCS model. And then for the density and the temperature, we have no clue. There's no measurements, no observations of that. So we just take some average values, typical values to do predictions. Of course, if you do a historic event, we have the measurements at 1 AU, and we can try to play with these parameters to fit the data better. But if it's a prediction in the future, we have no clue, so we just put an average density and an average temperature. And then for the magnetic field, actually, we have different procedures to try to derive the parameters for magnetic field. So from extra ultraviolet observations, there's a procedure described by Erika Palmerio, who is now at Berkeley. And then Nat Gopalswamy has a method to determine more or less the toroidal flux, but it's a kind of very rough estimate of the toroidal flux. Nevertheless, we get sometimes very good results. Like, for instance, in September 2017, there was prediction, an event, 2 small CMEs that were interacting with each other, and there was a huge magnetic storm that we never would have expected because of these 2 small CMEs. And then we did some simulation, and we tried to explain how this happened. So here you can see there's a negative BZ component. And so when we did 2 CMEs with the same orientation on 4th and 6th of September, we were able to kind of reconstruct. You see, the timing is not good, but we have the negative BZ component also in the simulation. It's kind of the same order of magnitude. And so this was actually explaining why there was a negative BZ component, even though the CMEs themselves were not so dangerous. And it turned out that the plasma, the 2 CMEs, they catched up with each other just before they arrived at Earth. And the plasma in between the 2 CMEs was kind of squeezed because of the interaction of these 2 CMEs, and that explained why there was a negative BZ component. We tried to visualize that with drawing magnetic field lines because we have a 3D calculation, so we can at any time plot the magnetic field lines, and you can see here the first CME, the flux rope, here the second flux rope, and then in between we got this negative BZ component, which is visualized here by the color scale. So the negative BZ component was in this case just because of the squeezing of the plasma between the 2 CMEs, which was kind of satisfying that you can explain, but also frightening because it means that the timing of two CMEs can also be cause a very dangerous effect at Earth. Paradise is our model that is developed by one of my PhD students, Nicholas Wijssen. It's also an acronym. It stands for Particle and Radiation Asset directed at interplanetary space exploration. And so this is a model for transport and acceleration of particles. So what he can do is he can plot the anisotropy, like you see here. This is the anisotropy, and here is the observer. You start a CME, and then at some point when the particles reach the observer, you start seeing the anisotropy, and then you can plot this profile versus time. So what Nicholas is doing, most of the SAP models, they use this Parker spiral, this analytic model for the field lines. But of course, as I showed you in the movies, the magnetic field lines are seriously disturbed by the coronal mass ejections. So the Parker spiral is just a very rough estimate of the interplanetary magnetic field. So what Nicholas does in his Paradise model is just first a Fourier simulation. He gets a good approximation of the magnetic field of the background sun and the CME, and on top of that, he uses that field lines in his SAP propagation model. So much more realistic simulations. Of course, it's solving the focused transport equation, which is derived from the Vlasov equation in mixed coordinates, kind of getting a bit complicated. But this is the equation that he solves. So we have mixed coordinates. So the position is expressed in an inertial frame, while the other the momentum here and the pitch angle or the cosine of the pitch angle are expressed in frame co-moving with the solar wind. So it does some simplification, of course. For instance, this term is dropped out, it's taking a gyrotropic distribution function. But the thing is that he can actually do some, he has to do kind of average, there's a stochastic part and an average part, and then he kind of writes the equation as a set of 5 stochastic differential equations. So this here you have these 5 stochastic differential equations where you take into account all the effects: convection, streaming, GC drifts, focusing, mirroring, momentum change, diffusion is taken here in the source time in the right hand side. And so pretty involved calculations, but also giving very nice results. For instance, here this is a very simple CME model on top of an artificial wind. And so here you have 3 observers. Here we will launch a CME. You have 3 of the purple, green, and orange observer. And so here we will plot the intensity of SAPs at the position of the observers. And if I start the simulation, you see the particles are accelerated, but they don't reach these observers. They first reach the purple observer, and only now it reaches the green observer. And you see the particle intensity going up at that position. And only now it reaches the orange observer, and then you see also this profile. We can produce these profiles for different energy levels and compare them then with observations, as I will show you in a few moments. We did very nice things. You can also get, of course, acceleration in other shocks, like for the CIRs, these regions between the fast wind streams and the slow wind streams. They also form shocks. There's a forward shock and a reverse shock even. And so you can get magnetic bottles forming, and then you can also get particles being captured in this magnetic bottle and being accelerated to very high energy levels. Actually, he did a kind of nice simulation there. He injected particles here, 4 MeV particles at the bottom of this fast stream in the wind, and then you can see here with and without cross-field diffusion. This was a study to see how cross-field diffusion would affect the simulation. And here you can see, of course, more particles going away in the direction perpendicular to the field lines when you take this cross-field diffusion into account. So there are a lot of differences with the other models, because other models use the Parker spiral, and here you see that you can have these long-lasting high intensities at small radial distance because of this magnetic bottle that is forming because of this interaction with this CIR shocks, which is not taken account, of course, in the Parker spiral. We also have the very small cross-field diffusion that has a very large effect on the particle distribution after some time. In fact, we could observe that without cross-field diffusion, we have this population that is centered around this reverse CIR shock, while if you take into account the cross-field diffusion, we have a second population that is centered on the forward shock. And in the observations, we see actually two populations. It was a big mystery why we see these two populations, but with this code, we were able to clarify this. So we have a big project going on now called EUHFORIA 2.0, making a new, more advanced version of EUHFORIA, and implementing or applying EUHFORIA to do some very complex CME interactions, and also coupling EUHFORIA to models for radiation and for these geomagnetically induced currents. Yeah? So we want to just improve EUHFORIA and make it available to the international community. So we want to get more advanced flux flow models. We also want to have a better global MHD coronal model, and we want to integrate SAP transfer model like Paradise into EUHFORIA in an integrated tool, actually. I just want to show you in 5 minutes a few results. We, in first instance, coupled an existing coronal model, because it's called multi-VP, which is actually based on a potential field source surface extrapolation, but solving the MHD equations along the open field lines. So much more physics than in the Wang-Xili arch model. And indeed, when we couple this model to EUHFORIA, we get much better modeling of the fast streams. So EUHFORIA is typically bad to or underestimating the velocity in the fast wind streams by 100 to 150 kilometers per second too slow. And with this better coronal model, MHD coronal model, we are actually able to model these fast wind streams better. Here you see with the Wang-Xili arch, you see this, there is no fast, these are equipotential surfaces of the velocity. There is no fast stream hitting the Earth is this blue dot, where here, when we take into account this multi-VP, this new coronal model, it actually hits the Earth. However, the multi-VP model is having a lot of physics, but it still takes 5 to 6 hours to converge, which is way too long. We cannot use it in an operational context. We need simulations really within 1 or 2 hours. So there is a big need for speed because we do not know, we do not do one simulation. Yeah. So there's too much uncertainty on the input parameters. I told you that there are 10 input parameters for the CME. Yeah. So and some of them are pretty good, like the timing, of course, and the longitude and latitude are pretty good. But for instance, the magnetic field, the magnetic flux is plus minus 50%. So it's a very rough estimate. So what you want to do is to kind of take these uncertainties into account by what they call ensemble modeling. So they do not do one simulation, but you do many simulations with different values of the input parameter between the error bars, of course. And then instead of predicting a time of arrival, for instance, you predict a window of arrival, and you say the shock will arrive in this time window with 90% certainty. That you can do when you do this simulation. But of course, if you have 10 input parameters and you would take 3 values per parameter, you have 3 to the power 10 simulations to do, which is like 50,000. This is too much. So we need to do now uncertainty quantification to see which of these 10 parameters are contributing the most to the quantity of interest, like the time of arrival or the shock strength or the BZ component. And we are doing this kind of simulations now.
Yeah, we'll also have to wrap up now, Stefan.
Yes,
we're running at 59, yeah. So maybe take a couple of.
I'll just 3-4 minutes. I just so we're also developing a new global MHD model. We have an unstructured grid mesh code with an implicit solver, and therefore we can do much faster simulation, because to a steady state we get very big CFL steps. Here it was like 800, but we can go to 10,000, and so very fast conversions, and we get very good results now with our model. It's a brand new model, and we are planning to use this as a model because it converges in 52 minutes. As normal global MHD models of the corona need 24 to 26 hours to converge because they are explicit. So they need hundreds of thousands of time steps. We can do it with 1,000 or 2,000 time steps and get a very good result, as you can see here. We also included adaptive mesh refinement. So also speeding up the code with different criteria. We can also, as you can see here, and so this is also giving a speed up of factor 28. So I'm not going to go to all the, I have too many slides, I think, sorry. So we also have a more advanced flux model implemented. So we are making good progress now in not getting better simulations faster and therefore more accurate predictions. Let me stop there. I was going to show you some other results, but let me just stop here.
Well, yeah, apologize, but I didn't record right at the start of the talk, but I'm recording the end. So if anyone needs to go and
no problem. I just had too much material. Oh, I talked too slow or too long about the intervention. Sorry.
Yeah, fine. No, we've got the recording, and so if people want to look over the questions or anything later, but if there are any questions now, then we can take those. Yeah, I think a lot of people had to leave for their 3 o'clock teaching and meetings. But yeah, I think one of the things that stood out for me throughout the talk was this kind of like fact that when you look at like the MHD equations, they look really idealized, and some of the aspects of the corona look quite idealized as well as you would draw them, these filaments and kind of like nicely smooth arching structures. But of course, we see lots of stochastic effects and lots of inhomogeneity in space and time, and you know, we're taught a lot about, you know, chaos theory being, you know, non-linear coupled dynamics generating these kind of things. Would you say that that's the main thing that's going on for generating all this kind of like uncertainty in your initial conditions, or is there like other sources of noise which are kind of more discrete?
Yes, of course. So they have the uncertainty of the input parameters. You also have the uncertainty in the model itself, of course. Indeed, we do not take into account all the physics. And even in the coronal model, you have some ad hoc heating terms for the corona because you don't know what is heating the corona. So we should also take that into account. And this would be probably done in the next step for this uncertainty quantification. We are doing some simulations now because we want to limit these ensembles. Yeah. So if you know the 2 or 3 parameters that are most important for the prediction of the BZ component, for instance, we can play with these 3 parameters instead of with all 10 parameters, you see. And that's what we are doing further, because it's we want to implement this ensemble modeling in our implementation in the modeling center. And then later on we will do, when we learn more about this uncertainty quantification, we will also probably try to quantify the uncertainties in the models in themselves. Yeah.
Yeah, I think we've got one question. Is it from Attila?
I have some questions. Maybe they are really random, but hopefully we can answer it. So one of them was that in the MHD equations, I would have expected that the electric field is also in there, but it wasn't. It's like, I don't know why. Maybe is it because of they just cancel out all these positive and negative charges, or?
No, that's a very good question, actually. No, if you do the dimensioning of the different terms, the electric field and the current density play a secondary role, because we, in the Maxwell equations, we actually use the pre-Maxwell equations. So we ignore the displacement current. Because the term with the displacement current is scaling like V over C squared, C with the speed of light. And so since V over C is a very small quantity, this term is not important. So in MHD, it's completely ignored. And so the electric field is then reduced to a secondary quantity because it's just minus V cross B. So you eliminate from the equations.
Yeah, that makes sense.
Yeah.
Okay, and the other one was that there was this like period, like 22 years period, like, is there anything, like, is there any reason why is it like 22 years or so? Like, is there any research on that?
There are people modeling the dynamo of the sun, and I don't know if there must be a reason, but it is a very good question. Why 22 years? And since other solar-like stars have a different periodicity, and also the period of the sun, by the way, changed in time. So you can see footprints of this periodicity in many things at Earth. For instance, also in the thickness of the rings in trees. And they have some very old, million-year-old trees, stones now, but so they can see that there's a periodicity in the thickness of the ring trees, the tree rings, I should say, tree rings. And so the young sun at a periodicity or a periodic cycle of only 7 years. So it changed during the lifetime of the sun, and that I don't think we can explain at this moment. But so there must be a underlying reason, but it has to do with the convection zone of the sun.
Yeah, there's something inside that just.
Yeah, there's so at the bottom of this convection zone there should be. We think there are very strong magnetic fields, like 50,000 Gauss strong fields, and these flux hubs are formed there, and then they rise due to magneto convection, and then they kind of go through the surface of the sun, where they see where they're formed in the sunspots, and so the dynamo models can go very far, actually, surprisingly far in explaining this. But I cannot answer your question. What is the basic?
No problem.
Cycle, but
I'm just wondering. I have a few more if I can do that.
Yeah.
I don't know if we have time.
Yeah.
Yeah, sure. This is just discussion time now. So.
Okay. So I was wondering about what's this slow and fast wind, because I think I missed it. Like how is it distributed in time and space?
So the slow wind is the one that actually starts in the equatorial belt, so in the active region of the sun, so where the sunspots are, so plus minus 30 degrees latitude. And so this has a different chemical composition also. And the fast wind actually comes from the coronal holes. These are open field line regions in the corona of the sun, and there the wind is much faster. We don't know why. We cannot explain the fast wind. The Parker model had only slow wind. Yeah, but
I was thinking like it maybe like I was thinking that it would be connected to the electric field.
Yeah,
but
like an
it's
accelerator.
like you have the charged particles, and then they are like.
Yes,
I don't know.
Probably, but why would the electric field then be larger in this coronal holes? We don't know. So there are several explanations involving magnetic reconnection and micro flares or nano flares, and you have many of them. But actually, these so far there's no model that can actually explain this. All observational facts about the fast and slow wind. This is one of the remaining problems in solar physics, actually, the acceleration and the heating of the corona also.
Yeah. The last question was there was this spherical model for some CME you mentioned. I don't know what was the name for it. This Spheromac. And then I was thinking maybe a cylindrical one would be better, because when it hits the Earth, and it's not really spherical, but it's like
so that's what we are trying to do. We actually also have toroidal CME models that we are now implementing, and I cannot show you results yet, but we expect that these might be better indeed. Yeah, it's just a bit more complicated to implement them, because for a sphere it's very simple, because you have to we implement them as a time-dependent boundary condition at the lower boundary. And so if you have the analytical solution, you can just program these functions in time. And for a toroidal solution, the one I showed you was actually a numerical solution. It takes much longer because you have to solve differential equations. But there is one.
I was thinking of like an infinitely long cylinder, but probably there's some analytical one there.
No, this is we have a toroidal solution. There is one analytical solution, Soloviev solution, that we are now implementing, and we will see if that gives better results or not. Yeah.
Okay, well,
okay.
That's all I have.
Okay, thank you.
I just had one more thing, and that was whether you've considered this idea of digital twin modeling, because it seems like you've got a constant need for forecasting. You've got some flaky not complete data sets coming through maybe live or with a delay, and maybe you could couple your modeling to those to try and constantly hone the modeling parameters. Yeah.
But what do you mean with digital twin modeling?
It's just this concept of live coupling a computational model with unknown parameters to real observations, and instead of assembling an ensemble of different simulation runs, which would have to be done in parallel, you're constantly tuning those parameters by the uncertainties relative to the model. It's kind of an attractor, if you will, for the model based on live data.
Yeah.
Yeah,
we tried some data assimilation. That is probably what you're meaning, or
yeah, I'm not sure on the data assimilation. So
I
yeah,
have to check. I don't know the term digital twin coupling, but I will check it, because there is an opportunity. They are going to launch now an L5 mission. Yeah. And
yeah,
so
the Lagrange farm. Yeah.
The Lagrange mission. So there it will be possible, because the wind at Lagrange is the same wind that will actually hit the Earth 1 week later. So that will be a big opportunity to improve our background wind model, because we will have in situ measurements, and the wind in this 1 week will not change too much. It just rotates. So if we can model that better, the background wind, we will have a big advantage. So that's what. Yeah.
So the idea with the digital twin, I think, would be that you would start your model with the 5 weeks ago reading as an initial condition, but you'd still have the live data from L5, and you'd see how your model's diverging away from that, to give uncertainty, but also maybe then tune your parameters and run against.
Yeah, that's a possibility indeed that we should consider. Yeah.
Okay, well, yeah, that was excellent. I don't think we've got any more questions, and yeah, brilliant. Thanks a lot for giving us a great talk. Okay. And I'll get the amount of stuff I had fully recorded onto YouTube. I'm sorry we missed the start, but hopefully that covered a lot of the technical aspect in the end.
Yeah. Okay. Thank you for inviting me to give this talk.
No worries.
Good.
Have a good day.
See you.
Bye.
Bye. Bye.